Good afternoon, sir.
Yeah. So in the previous lectures, we discussed some examples of matrix spaces. So let us revise quickly what we discussed in the previous lecture. And in case you have doubt, you may stop by me, and we'll discuss that. So we discussed some examples. So this example is regarding the L1, which is a vector space, that is a space of all sequences. So what is L1? L1 contains the element which are actually a sequence. So sequence means we can consider it as a function. So x is a function from natural number to real number, or the domain can be C depending on what we are taking. So that means x1, x2, xn, and so on. They are the either complex number or real number. And not only that, we are posing this condition that it should be absolutely convergent series. Those sequences x1, x2, x and so on, such that the corresponding series with modulus sign is convergent. So that is L1. Similarly, L2, we instead of mod x j, we take mod x j square, and then we consider L infinity, in which we take the supremum of modulus. So we have some of the property we have checked that this L1, L2, and L infinity are vector spaces where addition entry wise, right, or component wise we can say. And similarly we can define the scalar multiplication, that is k times x. uh, the scalar product of k and x is defined as k multiplied on the each of the component. We have checked that if we multiply k to each of the component, and if x belongs to L1, then k times x also belongs to L1. So that is this computation. So L1 is a vector space. Yeah. So and then this is a set of all sequences. What we have discussed is that the set of all sequences also with respect to addition and scalar multiplication, that is a vector space. So L1, L2, L infinity are actually subspace of this particular vector space. So that can be verified. So we already verified that L1 is a subspace. So that these two things we discussed, it is closed under addition and under scalar multiplication. Similarly, we can check it for L2 and L infinity. They are also a subspace. So there we will consider the condition of L2 and L infinity correspondingly. After that, we discuss the distance function. So if we have L1, L2, or L infinity, we can define distance function. Yeah, so here we are defining distance function for two elements of L1. So that is this function. And if we take xy belongs to L2, then we will consider the second function d2, which is a metric on L2. And if we consider x to be L infinity, then over this vector space we can define metric using the third function, d infinity. So this is just notation, d1, d2, d infinity is metric, but it corresponding to these spaces. So therefore, corresponding to L2, we are denoting d2. Okay, and then we seen some examples which elements belongs to some trivial elements which belongs to L1, which does not belongs to L1. Similarly, in L infinity and L2. And one more example we have discussed, this is also a subspace of the sequences. C00, and this C00 is actually a subspace of C0, and C0 is a subspace of all sequences. All sequences. So this C0 means all convergence sequences which converges to 0. So there are many vector spaces which we can discuss using the sequences itself. We will mainly focus on this L1, L2, and L infinity. So here we have discussed that this on L1 we can verify the properties of D1, that D1 is a metric on L1. Right? So that is what we discussed in the previous lecture. We will not go into more details. Similarly, we discuss D2 is a distance on L2, vector space L2. Right. So we use these inequalities here, Minkowski and Cauchy squares. And at the end, the last example which we discuss is a slightly different example, that is a function. So L1, L2, Ln has elements which are functions from natural number to C. Right, that is what we discuss here. These are the functions from natural number to complex number, which are elements of L1, L2, and L infinity. But here now we are considering any arbitrary set T, and for this set T, we are considering the function x from T to K. So usually we use notation f from T to K, but uh, in this Lemaister book, he is using x symbol for functions. Right? So do not confuse with this. These are only functions which are bounded. So bounded means there is a x that f modulus f t is less than equal to that fixed number for every t. So such a functions are bounded, and they are k valued function. So that means basically we are considering k is either real number or complex number. So clearly Bt is a vector space, and we add point wise. So x plus y at t is xt plus yt, and similarly scalar product we can define, and the metric we are defining is this metric. So clearly this matrix satisfies all the properties of the distance. For example, distance of xy is distance of yx, because modulus of xt minus yt is equals to modulus of yt minus xt. Right. So d infinity xy is same as d infinity yx. Similarly, if d infinity xx is 0, that is clear because modulus xt minus xt is 0 for every t, right? So this is 0, so its supremum is 0. Distance of xy is 0, that means supremum is 0. Supremum is 0 means each entry is 0, that means xt is equals to yt for every t, right? And if xt equals to yt for every t, that means x is equals to y, the same function. X and y are the same functions. And last property we can check, which is a triangular inequality. So if you remember, we discussed this example earlier using where we have discussed that d infinity is the distance over kn, right? So this is the same example, but here instead of maximum, we are taking supremum. So just we need to modify this definition, that idea here, and we can easily show that this is a satisfies the triangular inequality also. So you can try this as an exercise that show that the infinity is a metric. You can see it might have given in some book also explicitly. So if you find any problem, you can refer to some book. So in particular, if we take t is equals to natural numbers, then pt is exactly the, so as I said, it is L infinity, right? And the operation are also pointwise addition and scalar multiplication on L infinity and bt. So as a vector space, these two are same if we take t is equals to natural numbers. In that sense, bt is a generalization of L infinity, because in general we are defining for any non-empty set t. Okay, t is any non-empty set, but as a special case we are getting L infinity. Okay, after that we discuss the sequence convergence, and then we discuss that if we take p belongs to 1, 2 or infinity, and LP is a metric, on LP, if we define the metric dp, then the convergence xn converges to x in L1. That means this first distance of xn and x goes to 0, and that means this. So here we have discussed the definition of d1, right? Similarly, for L2, if this sequence converges in L2, so what is this sequence? This sequence is basically the function. Each xn is a function, which, so what is xn? Xn is a function from set of natural numbers to k. So if xn converges to x, so that means this function converges to x from n to k if this happens. So that is this condition. So meaning of that is this one by the definition of d1. Similarly, the function xn belongs to L2 converges to function x belongs to L2 if second metric, with respect to second matrix, it converges to 0. And then using the second metric definition, we are getting this condition. And the last one is the d infinity matrix. And in the infinity matrix, that means if xn converges to x in L infinity, d infinity xn comma x converges to 0, that means we get this condition. And this condition is nothing but if we convert into epsilon and not definition, because this is a sequence actually, and it converges to x, right? So this converges to x means this model section j converges to xj for every j as n tends to infinity. So xnj is what? Xnj is a number, complex or real number. Similarly, xj is a complex or real number. So now we have a sequence of complex and real numbers which converges to complex or real numbers. So that we know that this xnj is a sequence. So in between we can write a step that this means xnj, which is a sequence that converges to xj for every j belongs to n, every natural number. So now this is a sequence of real or complex numbers, so you can use convergence of sequence. So that means for every epsilon greater than 0, there exists n naught that x, this happens for all j and after some n naught, n is greater than or equals to n naught. So since it is happening for supremum, so it holds for every j, right? Because supremum is like maximum. So this is less than greater than equals to xnj minus xj. Xnj minus xj is less than equals to maximum of this. So maximum is basically here the supremum we are taking. So here we are taking for particular j, but here we are taking supremum over all j. So that is bigger. And if this is less than epsilon, then this will also be less than epsilon because it is smaller than supremum. Right. So now this thing we have written here that is less than epsilon, and that holds for every j. So now this criteria is basically the uniform convergence. Xn, which is a sequence of functions, this is a function, it converges to this function uniformly. Uniformly means what? Uniformly on the set of natural numbers on the domain. Okay, so yeah, so any doubt so far regarding this? Okay, so then let me start the new things today. So in each of these three things, what we are getting. So if we take xn converges to x in L1, we get this criteria. And so let me call this 1, this we call 2, and this is our third condition. So this is convergence in L infinity. Second equation is convergence in L2, and the first condition is xn converges to x in L1. So in it, xn converges to x in L1, L2, or L infinity, any of them, then from equations 1, 2, and 3, it is easy to observe that xn j converges to xj as n tends to infinity, right? Each fixed j belongs to n. We get this. So is it clear that if we take equation 1, then we can show this? For example, xn1 converges to x1 as n tends to infinity. But if this is true, that summation j1 to infinity xn j minus xj converges to 0 as n tends to infinity, can we say that xn1 converges to x1 as n tends to infinity. So what is the relation between these two? This converges to 0. What can we say about this? Whether this converges to 0? Yes, Jayesh, any idea?
Sir, if we can apply some property of like partial sums, mm,
Yeah, partial sum we can apply, or basically what is this?
this
This
is a
series.
infinite
Yeah.
sequence.
So what is that? If we take j is 1, then this is this term. What is the second term? Right. So now this series is this summation. What can we say about this one and this one? How they are related? So this is basically the first term of this series. So the series goes to 0, then this is the first term. This is a series of non-negative terms. So we know that this is always bigger than this, right? So this is less than equals to this, and this converts to 0, right? This is always non-negative. So that will give us xn1 converges to x1. And there is no speciality about 1. We can do this for 2 also, and in general we can do for any fixed j, right? So this is true for every j, fixed j. Right, so this thing we have done for the whenever the first equation is satisfied. But we can also check this for the second equation, because the second equation is nothing but it involves the square term, right? So if it involves a square term, again the same idea we can use, and we can show that xn1 minus x1 square converges to 0. And if xn1 minus x1 square converges to 0, then xn1 minus x1 modulus also converges to 0, right? And because we can take square root of the convergent series, so that also converges if it is a non-negative term series, non-negative term sequence. So that will also converges to 0. So from 2 also implies the same condition, that x and j converges to xj. And here it is more simple because of this thing, right? So if this converges to 0, then obviously x and j minus xj converges to 0. Okay, so this is the reason behind why this holds. what this result says that if the sequence of functions xn converges to x either in L1, L2 or L infinity, then it converges coordinate wise or entry wise, right? Each jth coordinate converges to jth coordinate of x. Okay, but now what about the converse? So conversely, so let me write down what we proved just now. So this means xn minus xn converges to x in LP for p belongs to 1, 2 or infinity, implies that x and j converges to xj for each j belongs to n. So this is entry-wise convergence. Conversely, a converge is not true. So to see the converse, we will see the functions which are generalization of E1, E2, En. So we know that E1, E2, En are the uh, orthonormal bases of Rn or Cn, right? So that we remember it is 0, 0, 0, 1, 0, 0. So nth coordinate is 1, other coordinates are 0. So that we will generalize here. So for example, we use notation En, which is the, so each En, each xn is basically a function defined on natural number. So it is a sequence. So that means En is the sequence 0, 0, 0, 0, 1, 0, 0, so on. Right. So this one will come at the nth place. Right. So we can also define this same En. So in other words, En is a function from natural number to k such that En defined on some natural number j as 1 if j is equals to n and 0 if j is other than n. Right. So that is the same function. So now this function En, which we want to show that what can we say about whether it satisfies this property or not, right? So for that we'll fix some jth coordinate and we will see En of j, where does it converges. For that, let some fixed number j belongs to n. So what is Enj? Enj we already defined here, right? So Enj is basically this sequence, right? Enj means jth coordinate. So if take n tends to infinity, then where does this converge? So for example, we fix j, so j is equals to 2. Then what is E1 of, yeah, so what is En of 2, if you take n is 1, then it is 0, right? If you take n is equals to 2, it is 1, n is equals to 3, it is 0, n is equals to 4, it is 0, and so on, right? So because this function is basically kind of direct function, so if whenever these two are same, that then only the value is 1, otherwise it is 0. Now we can see that if n goes to infinity, the value is 0 for the large n. So that means En converges to 0 for 2. Similarly for 3, for any fixed number, Enj converges to 0. Right. So for any fixed coordinate j, Enj converges to 0. So that means entry wise it converges. Right. So now entry wise it converges to some number, right? So now using this we can define xj. So what is the xj? Xj is basically this. If you define this xj, then the corresponding function we are getting is 0 is equals to 0, 0, 0. Right? x1, x2, xn. Each of them are 0. So this we are getting this function, which is basically a sequence. So now question is En converges to this 0? So that is the converge of this. If xn converges to x in L1, L2 or L infinity, then it converges entry wise. Now we know that En converges entry wise to this 0 sequence. So the question is whether En converges to 0 in L1, L2 or L infinity. So for that, of course, what we need to do is we need to find the metric En with 0, 1, 2 and infinity. So what is the first distance? First distance is summation j1 to infinity modulus of Enj minus 0 at j. 0 at j means jth coordinate of 0 sequence. So that is anyway 0, right? So it's nothing but modulus of this. Second distance is the same one with modulus Enj square. And the third one is supremum of modulus of Enj. So now we can use the definition of Enj. So Enj is the function whose only one entry is non-zero, other entry is zero, right? So if we take modulus of each entry and add them, that is the first metric, right? Modulus of each entry and adding them, so that is one only, right? Because only one entry is one, other is zero. Similarly here, we will take modulus of each entry of En, squaring that and adding them. So again, only one entry is 1, other entry is 0. This also is 1 because 1 square is 1. And here also, you can see that only one entry is 1, other is 0. So taking modulus, there are only two entries, 0 and 1. So supremum is maximum of 0 and 1. So that is 1 itself. Right. So in three of these, we can see that this doesn't convert to 0, right? In fact, yeah, similarly, this is not converged to 0, does not convert to 0. Right. So as n tends to infinity, we are discussing. So for each fixed n, distance is 1. So in fact, it is converges to 1 as n tends to infinity. So it is not converged to 0, but En converges to coordinate wise, it converges to 0. But with respect to these three matrix, it is not converged to 0. So that means the convergence in D1, D2, and D infinity matrix is stronger convergence than the convergence in entry wise. So that is what we observe here. Okay, now we have discussed, we have come across some notions of matrix space where we know that we can define closed set, open set, and all these things in matrix space. So let us revise some of the definition quickly. If X is a matrix space, a subset E of X is called closed set. So what is the definition of closed set in matrix space? So we can use sequences here, right? So basically, all the limit points belongs to the set, then it is a closed set. So that we can define using sequences. So if Xn is a sequence of elements of E which converges to X belongs to X. What is X? X is the matrix space, E is a subset of X. So if we take any sequence in the subset which converges to elements of the set, then X must be in E. Right. So if this criteria is satisfied, then we say that E is closed. And in other words, we can use also the definition of the closure of set. Right. So if E is is a subset of X, then the closure of E is defined by, so E closure is basically the set of point X in X such that X is the limit of Xn. So basically X is a matrix space. So here limit we are taking with respect to that particular matrix, and where Xn is an element of E. So now using closure also we can discuss the closed set. So if E is equals to E closure, then E is closed. Right. So this is another criteria. And in other words, converge is also true in matrix spaces, that if E is closed, then E is equals to E closure. That is also coming directly from the definition itself. So this is if and only if characterization of the closed set in matrix spaces. In general, in topological spaces, you will see that this may not be true because topological spaces there is no metric, right? So there are examples. Okay, and if you know the closed set, we can define the open set as a complement. So a subset A of X is open if X minus A is closed. So these are the definition of open and closed set. And now we are interested in the basic open sets. So basic open set means the balls. So for X in X and R greater than 0, consider the open ball. So some books use this set as a BXR, right? Because it is a ball, but we will be using notation UXR. UXR is basically the set of all points in the matrix space such that distance of X with Y is less than R. Right, so we already know one simple example of R2. If we take X equals to R2, and if we take with respect to the first metric, so with respect to first metric, the open ball is R2 means we have two coordinates y1, y2, that is element of R2, so that the metric, first metric of X and Y. So that means we need to take another element of R2. So D1 of first element is X1, X2, its distance with Y1, Y2 is less than R. Yeah, but here we are taking R is 1, right? So radius we are taking 1. So this is essentially, if we simplify y1, y2, basically they are real numbers such that the first metric, what is the first metric? First matrix is summation j1 to 2 modulus xj minus yj less than 1. And actually we are taking the vector x to be 0, 0, right? Because we are taking distance with 0, so 0 means the origin. So x1, x2 is 0 here. So general element it is this one, but with 0, 0, if we find the matrix, it is yj is less than 1. Right, so if you simplify this, it is y1, y2, two coordinates, so that modulus y1 plus modulus y2 is less than 1. So we are taking xy plane, but metric we are not taking Euclidean metric. We are taking first metric, right? So therefore we are getting this set. So now this is the first matrix. Let us find out the second matrix, which we already know. So that is basically what we get is y1, y2 such that square, right? So y1 square plus y2 square less than 1. What is shape of this set? Geometrically, it is a interior of unit circle, right? Because this is a equation of circle inside circle. But this shape, what it will be? Now, infinity means it is a maximum of the difference of coordinate, right? So that means it is a maximum of modulus y1 minus 0. So that is modulus y1, and modulus y2 minus 0, that is modulus y2. Right. So what we are using is we defined d1, d2, d infinity on kn, right? So that is what we are using here. K is r and n is 2. So what is shape of this? Right. So here we know the shape is inside unit circle. So here if you find this, we have two coordinates y1, y2, and the value of y1, if you take y2 is 0, then we get modulus y1 less than 1. So that means y1 is between minus 1 and 1. Similarly, if you take y1 is 0, we get y2 to be from minus 1 and 1. Right. So we get from minus 1 to 1, 1 to minus 1, right? And if y1 is increasing, then y2 will decrease. So basically we will get this shape. So interior of this diamond, that is this shape. Geometrically it is this set, and the last one is this maximum. So here what we get, the shape will be kind of a square. Because modulus y1 can also be, we can take up to 1, modulus y2 also we can take up to 1. So that means we draw this set in the xy plane, then that is all elements in this set the graph is this one, that is interior of the set, right? So depending on what is your metric, the open, this ball is known as open unit ball, right? That is what we call in usual Euclidean metric. This is a open unit ball with respect to Euclidean metric. But the same thing is here for the open unit ball with respect to D infinity matrix is has this shape, right? So it is not a circle, but it is a square, unit square kind of thing. And if you take the D1 metric, then it is a diamond shape. So geometrically, the shape of the unit ball depends on what is your metric in R2. So in general, this how do we define the open set in using the ball? So a subset E of matrix space X is open if and only if for every element in E we can find a radius such that the open ball about X with radius R is a subset of E. Right, so such a set is known as open ball about X with radius R. Right, so that we know that if we have a metric space and we have a set which is open, so E is open subset of X if there is any element X in E, we can find a open ball which has center X kind of thing and radius R. Right, so around every point X in E we can find U X R for some R. Yes.
Sir, I have a question. Sir, why this definition of open set got changes when we define on a topological spaces?
It is not different, it is generalization basically.
So because sir, in the topology, sir, every set belongs to the tau, which is a subset of X, isn't said to be open, sir. But sir, it is very difficult to imagine a topological space, sir. Everything is continuously changes in the topological spaces as compared to the real lines.
That is what is all about that course. You need to learn only that thing. So usually it takes time in understanding that course because basically what is topology is that topology is generalizing the properties. So let us start with some idea about topology. So properties of open sets. So if we have a real numbers or metric space, then we know certain properties of open set. What are the properties? First is phi and x. If x is a metric space, then phi and x are open sets in X. Second property about open set, we know that if we have an arbitrary union of open sets, then arbitrary union of open sets is also open set in X. Right? What is X? X is a metric space. So you can consider R2 or R or Rn. X equals to that basically, and Now we know the other examples of X also, that is L1, L2, L infinity. And the third property we know is a finite intersection of open sets is also an open set. So if we know matrix space, then we know what are the open sets in that matrix space, because we can find using metric what are the open balls, and we can find open set. So what is open set? Open set is basically arbitrary union of balls. So if we have a real line which is a matrix space, what we have is, we have what are the balls in real line? Yes.
Oh, sir, intervals.
हाँ इंटरवल होगा, तो ये कौन सा होगा? सो सेंटर एट 0, रेडियस 1, तो ये होगा ना, right? Because we have a real line, center is 0, radius is 1, so here length is 1. So how do we define this? We define as a y such that distance of 0 and y is less than 1. So that is basically, here distance is modulus, that is less than 1. Actually, that is this side. Okay, so what is the intervals? Intervals are basically the simplest open sets. And what are open sets? Open sets are basically how we define open sets in R.
Every point must be the interior point.
No, in terms of interval, I'm asking.
So
The
let
same thing
X
you are
be a
saying.
set.
Yeah. Same thing
Let
what you are
X be a
saying.
set, then X will be open set for if for all delta greater than 0, A minus delta A plus delta must be in subset of S. A belongs
So
to X.
basically what you are saying is that it is a union of intervals, open intervals. Right, every point is an interior point in that set. That means basically it is a union of interior point, means around every point we can find a neighborhood. So basically that set is a union of neighborhoods. So that means it is a union of open intervals. Yeah, so the same thing is generalized in topology. What is topology? Topology we are taking is any arbitrary set in which these three properties satisfied. So the collection of sets in subsets of X which satisfies these properties, they are called open sets. And there we have the notion of basis. What is so in real analysis, what is basis? Bases are intervals. And what are the open sets? Open sets are nothing but union of intervals. So this is basically the motivation of topology. Yeah, so you need to see some examples, then only you will get all these things. It will take some time. Anyway, so this is the properties. These three are the properties of open sets in matrix space. And then once we have the notion of closed set and closure, we can define the dense set. So a subset E of X is called dense in X if the closure is X, right? So that means now we know the definition of closure. So closure we define in terms of sequences. So that means for every X in X, there exists a sequence Xn in E such that Xn converges to X. Right, so this is the definition, this is the meaning of the E is dense in X. So we know that rational numbers are dense in R. They satisfy this property. So if you take any real number X in R, there is a sequence of rational number which converges to that particular real number. And there is a notion of separability. So X is called separable if it has countable dense subset. Yeah, so real set of real number is separable or not?
Yes, sir.
Yeah, it is separable because the
Set of rational number is dense in R.
yeah, so that is an example. So set of rational numbers are countable set, and that is a dense in R. Okay, so this is regarding the separability. Similarly, we can define the Cauchy sequence. Convergent sequence we already defined in matrix space. Similarly, we can define Cauchy sequence. So Xn converges, Xn is Cauchy sequence in a matrix space X. If for every epsilon greater than 0 there exists natural number such that Xn and Xm, the distance between them is less than epsilon for all n and m greater than equals to capital N. Okay, and we know that every Cauchy sequence is bounded. Bounded sequence means so Xn is bounded if there exists X belongs to X and R greater than 0 such that distance of xn with x is less than r for all natural number. So this is basically the usual bounded sequence in real line. Whenever distance of xn minus x less than r in real number, that means modulus of xn minus x less than r. So that means xn belongs to the set x minus r to x plus r. Right. So it belongs to this open set, each xn. So in fact, we don't need, yeah, for every n we can do that. So after some stage it is bounded, then also we can find the maximum and the same definition works. But that is same as this definition. So every Cauchy sequence is bounded. So converse is not true. We know the example. Right. So example is in R we have xn is equals to minus 1 power n, which is a bounded sequence. It is not Cauchy sequence. Now we know that every convergent sequence must be Cauchy. Right. Every convergent sequence in a metric space must be Cauchy sequence. Converse is not true. So do you know an example of a metric space in which you have a Cauchy sequence which is not convergent? So example is very simple. So take any non-closed set. For example, we know that R is closed, but in the set of real numbers, if we take the subset which is open 0 close 1, and since we are taking it is a subset of real line, we are taking the usual metric on R, the standard metric modulus. Yeah, so basically we are taking distance of xy is modulus x minus y. So with respect to this metric, this is a subset of R, so it is also a metric space as a subset, and in which consider the sequence. So we'll take a sequence whose which is converges to 0. So for example, we are taking 1 upon n sequence. We know that it converges to 0 in R, but 0 is not in this set, right? Because it is not closed basically. So then xn is a Cauchy sequence in X, but xn does not converge, in X, because xn basically is converged to 0. 0 is outside X. That is the reason. And so basically, which property is being failed in this set X? That property is known as the completeness. Right. So completeness metric space in which every Cauchy sequence converges is called a complete metric space. Right. So we know that the example is R with the usual metric. Right. So R with the usual metric is complete. And in this course, we shall see that L1 with respect to D1 matrix, L2 with respect to D2 matrix, and L infinity with respect to D infinity matrix. So these three are the matrix spaces. We'll see that these three matrix spaces are complete. Right. So this we'll see later. What is the proof that we'll see later? Okay, so this is the story of some results of matrix spaces which we wanted to discuss. Now let us see the relation between metric and norm. Just a minute. Metric and norm. So if we have a metric, we will always correspond to metric with norm. So for example, this is an example that if we have a norm which is modulus, we can get a metric, and if we have a metric that is mod x minus y, using that we can define modulus of x. So both of these things are related to each other. So what is the definition of norm? So a vector space X. So I'm not writing every time non-empty vector space, but obviously it is a non-empty set that is a vector space, and mostly we'll take non-zero vector space. With the function that is known as norm. So norm is a function from X to R satisfying the properties. First property is norm of every element should be non-zero. Norm is 0 if and only if X must be the zero vector. Second property is modulus of Kx is modulus of K. Right, so this is true for all X is element of X basically. So this is modulus k times norm x for all k in k, x in x. And the third property is triangle inequality. Fine. So this property is satisfied, then we call it a norm, and vector space along with the norm is called a norm linear space. So if we have a norm, we can define metric, and the relation between norm and metric is, so every time if we have a metric, we will define the norm using this relation, and if we have a norm, we will define the metric, vice versa. So what is the example? Example is, we know that the matrices. So the first example is L1 D1. Yeah, so norm, how we define norm? So basically norm of x is distance of x with 0, right? Norm of x is what? If you take y is 0, you get distance of x with 0. So this way we can use metric and define norm. So in L1, if you take any sequence, so x equals to x1, x2. In L1, then what is norm in L1? So norm in L1 will denote by L1. So that is defined as d1 of x with 0. So 0 means 0 sequence, right? That we already know. That is, all entries are 0. So by definition, this is modulus xj minus 0. So that is modulus xj, j running from 1 to infinity. So this is one norm, basically. Similarly, in the metric space L2, D2, if you take the sequence, then it's two norm we can define as, again, distance, two distance of x with 0. So that is basically summation. Now we can write directly, right? So instead of modulus xj, we have xj square. And the third norm is L infinity norm. So infinity, yeah. So if you take any element in L infinity, all right, so that means basically its supremum is finite, supremum of modulus is finite. So then the sup norm, so this is known as sup norm, is defined as supremum of so infinity distance of x and 0, so that is supremum of modulus of xj. J belongs to the set of all natural numbers. So since D is a metric, we can use all its properties to verify that this function satisfies the properties of norm. That is a quite trivial. Yeah, so every norm gives metric, every metric gives norm, and there is a trivial example of metric. We know that on any set we can define discrete metric. So XP any set. We can define the metric. Right. So this is a metric that we can check easily that it satisfies all the properties of metric. But this metric will not give norm on X. Why that is true? So which property fails? So if you recall that we are taking here vector space, right? Because we need X is a zero vector. And in every set that may not be zero vector, right? So basically even addition and all those properties also we need here, right? So only on a set we cannot define norm, but if we have a metric defined on a vector space, we can define norm. So therefore we are discussing the norm linear spaces. Okay, so I think let me stop here today. So next lecture I will start some definition related to inner product.